Welcome to The Explainer. Today, we're enthusiastically setting the stage for a seriously high-stakes journey right into the mechanical heart of a ship. We're talking about the feed system, which is absolutely the lifeline of a marine steam plant. If you've ever wondered how these massive vessels handle incredibly high pressures and temperatures without their boilers just tearing themselves apart, preventing the exact overheating failure we covered in our last episode, well, you're in the right place. We're going to break down how this brilliant system works, step by step.
Okay, let's dive into this. It might sound a little dramatic, but it's pure engineering reality. Every single drop of water in a steam plant is incredibly precious. And it's not because water itself is expensive. It's because pure water is what keeps that massive boiler alive. The feed system's real job isn't just moving liquid around, it's actively protecting it. A single contaminated batch of feed water can scale up those boiler tubes. Once that happens, heat can't escape, the tubes overheat, and suddenly you're looking at a catastrophic boiler explosion. So for the ship, water purity is literally a matter of survival.
What's really fascinating here is the sheer number of invisible enemies this system is constantly fighting. We reuse the water in these plants because making fresh, boiler-grade water from scratch out at sea continuously is just way too expensive and inefficient. But while reusing water is highly efficient, that reused water accumulates threats every single cycle. We're talking dissolved gases, dissolved solids, and chemical contamination. So what looks like a simple plumbing loop is actually a relentless continuous purification line disguised as plumbing. It fights these invisible threats every single cycle just to keep the system safe.
Let's map out the chronological journey of just a single water droplet as it travels through this system. Think of it as a closed, endless circuit. First, it leaves the turbine as exhaust steam. Second, it hits the condenser where it shrinks back down into liquid water. Third, it moves over to the deaerator to get scrubbed of those dangerous dissolved gases. And finally, fourth, it's shoved right back into the extreme high-pressure environment of the boiler, ready to do it all over again.
Section 1. Creating the vacuum and transforming steam.
So, the condenser. Once exhaust steam from the turbine enters this regenerative condenser shell, it hits bundles of tubes cooled by freezing cold seawater. Think of it like a giant cold water radiator, but in reverse. Instead of a fan cooling a hot coolant, cold seawater running through tubes cools down that hot steam. The steam condenses instantly, physically collapsing back into liquid water. And as it changes state, its volume shrinks so dramatically that it creates a vital, massive vacuum inside the shell.
To really put the sheer precision of a mid-sized plant condenser into perspective, check out this number, minus 0.9 bar gauge. That's over 700 millimeters of mercury vacuum. That is an intense vacuum. And because that pressure is so incredibly low, the liquid condensate collecting at the bottom has to be drawn out by highly specialized extraction pumps. Those pumps have to handle very low suction pressure to pull the condensate out without failing.
Section 2. Extracting invisible threats, essentially the immune system.
Meet the air ejector. You see, even in a tightly sealed system, air and non-condensable gases somehow leak in or get dissolved in the water. This device uses high-velocity steam jets to create a Venturi effect, basically a super powerful suction force that continuously pulls those trapped gases straight out of the condenser. This is absolutely crucial because trapped air just doesn't condense. If it builds up, it completely destroys the delicate vacuum that the whole cycle depends on for efficiency.
Let me just pause right here and ask a quick question to challenge how you think about the system's vulnerabilities. Imagine you're the duty engineer. If your condenser vacuum slowly starts dropping, and you can completely rule out a seawater leak, what breaks first? What system should you suspect?
The answer? The air ejector. If its nozzles get blocked or its steam pressure drops, it stops pulling those gases out. The vacuum degrades. And I've got to warn you, losing even a tiny fraction of this vacuum isn't just a minor annoyance. It forces an emergency reduction in turbine load. The turbine literally relies on that vacuum to do any useful work at all.
Section 3. Stripping dissolved gases and fighting corrosion.
And this brilliantly illustrates the difference between what we've just seen and where we're going. We just described the condenser as a reverse cold water radiator, right? Well, the deaerator works exactly like an open soda bottle in a warm room. It's a completely different approach. The goal here is to use heat and agitation to drive dissolved gases completely out of the liquid, exactly like fizz escaping from warm soda.
Inside the deaerator, it's a wildly intense physical environment. The incoming water gets sprayed aggressively downward directly into a rising cloud of steam. This is direct contact heating. The extreme heat and violent agitation force dissolved oxygen and carbon dioxide right out of solution. It literally boils them off, so those aggressive gases can escape before they ever have the chance to reach the boiler and cause devastating corrosion.
Section 4. Return to the boiler. Extreme pressure ahead.
So the crucial point is this metric, parts per billion, not parts per million, parts per billion. That number really anchors the sheer scale of purification required here. The feed system has to strip that aggressive oxygen out so thoroughly that we measure the tiny bit left over in parts per billion, just to officially declare the feed water boiler safe.
Now, to actually get this flawless, de-aerated water back into the boiler, it has to overcome massive pressure. That's where the turbo feed pump comes in. This is an incredibly powerful pump, often driven by its own dedicated small steam turbine, that takes that clean water and practically shoves it against the immense, full working pressure of the boiler to complete our loop.
So, zooming out to look at the whole picture, turbine exhaust to the condenser, through the deaerator, into the boiler, and then the loop just restarts. It's a closed, never-ending cycle. This continuous purification loop runs relentlessly to keep the ship alive, constantly cycling to protect that boiler. But I want to leave you with one final, provocative thought today. If this relentless, high-pressure purification loop is the absolute lifeline of the ship, what happens to the vessel if the massive pumps powering it suddenly lose all electricity? A blackout at sea doesn't just turn off the lights, it completely stops the heart of this entire system. That critical dependency is exactly why electrical systems are so vital, and it leaves us with the perfect jumping-off point to explore the electrical grid next time. Keep questioning how things work, and I'll catch you in the next explainer.